This lecture is about the specific smoothing methods for language models used in probabilistic retrieval model. In this lecture, we will continue the discussion of language models for information retrieval, particularly the query likelihood retrieval method. And we're going to talk about the specific smoothing methods used for such a retrieval function. So this is a slide from a previous lecture where we show that with query likelihood ranking and smoothing with the collection language model, we end up having a retrieval function that looks like the following. So this is the retrieval function based on these assumptions that we have discussed. And you can see it's a sum of all the matched query terms here. And inside the sum, it's the count of the term in the query and some weight for the term in the document. And we have TF, IDF weight here, and then we have another constant here in the end. So clearly, if we want to implement this function using a program language, we still need to figure out a few variables. In particular, we're going to need to know how to estimate the probability of a word exactly, and how do we set alpha. So in order to answer these questions, we have to think about this very specific smoothing methods, and that is the main topic of this lecture. We're going to talk about the two smoothing methods. The first is a simple linear interpolation with a fixed coefficient, and this is also called a Jelinek-Mercer smoothing. So the idea is actually very simple. This picture shows how we estimate document language model by using maximum likelihood estimate that gives us word counts normalized by the total number of words in the text. The idea of using this method is to maximize the probability of the observed text. As a result, if a word like network is not observed in the text, it's going to get 0 probability, as shown here. So the idea of smoothing then is to rely on collection language model, where this word is not going to have a 0 probability, to help us decide what non-zero probability should be assigned to such a word. So we can note that network has a non-zero probability here. So in this approach, what we do is we do a linear interpolation between the maximum likelihood estimate here and the collection language model. And this is controlled by the smoothing parameter lambda, which is between 0 and 1. So this is a smoothing parameter. The larger lambda is the more smoothing we will have. So by mixing them together, we achieve the goal of assigning non-zero probabilities to a word like network. So let's see how it works for some of the words here. For example, if we compute the smooth probability for text, now the maximum likelihood estimate gives us 10 over 100, and that's going to be here. But the collection probability is this. So we just combine them together with this simple formula. We can also see the word network, which used to have a 0 probability, now is getting a non-zero probability of this value. And that's because the count is going to be 0 for network here, but this part is non-zero. And that's basically how this method works. Now, if you think about this, and you can easily see now the alpha sub d in this smoothing method is basically lambda, because that's, remember, the coefficient in front of the probability of the word given by the collection language model here, right? Okay, so this is the first smoothing method. The second one is similar, but it has a dynamic coefficient for linear interpolation. It's often called Dirichlet-Pry or Bayesian smoothing. So again, here we face the problem of a 0 probability for an unseen word like a network. Right? Again, we will use the collection language model, but in this case, we're going to combine them in somewhat different ways. The formula first can be seen as an interpolation of the maximum likelihood estimate and the collection language model as before, as in the JM smoothing method. Only that the coefficient now is not a lambda, a fixed lambda, but a dynamic coefficient in this form, where mu is a parameter. It's a non-negative value. And you can see if we set mu to a constant, the effect is that a long document would actually get a smaller coefficient here. Right? Because a long document will have a longer length, therefore the coefficient is actually smaller. And so a long document would have less smoothing, as we would expect. So this seems to make more sense than a fixed coefficient smoothing. Of course, this part would be of this form, so that the two coefficients would sum to 1. Now this is one way to understand this smoothing. Basically, it means it's a dynamic coefficient interpolation. There is another way to understand this formula, which is even easier to remember, and that's on this side. So it's easy to see. We can rewrite the smoothing method in this form. Now in this form, we can easily see what change we have made to the maximum likelihood estimate, which would be this part, right? So normalize the count by the document length. So in this form, we can see what we did is we add this to the count of every word. So what does this mean? Well, this is basically something related to the probability of the word in the collection. And we multiply that by the parameter mu. And when we combine this with the count here, essentially we are adding pseudo counts to the observed text. We pretend every word has got this many pseudo counts. So the total count would be the sum of these pseudo counts and the actual count of the word in the document. As a result, in total, we would have added this many pseudo counts. Why? Because if you take a sum of this one, over all the words, then we see the probability of the words would sum to 1, and that gives us just mu. So this is the total number of pseudo counts that we added. And so these probabilities would still sum to 1. So in this case, we can easily see the method is essentially to add these as pseudo count to this data. Pretend we actually augment the data by including some pseudo data defined by the collection language model. As a result, we have more counts. Right? So the total counts for a word would be like this. And as a result, even if a word has 0 count here, let's say if we have 0 count here, and then it would still have non-zero count because of this part. Right? So this is how this method works. Let's also take a look at some specific example here. Right? So for text, again, we will have 10 as the original count that we actually observe, but we also add some pseudo count. And so the probability of text would be of this form. Naturally, the probability of network would be just this part. And so here you can also see what's alpha sub d here. Can you see it? If you want to think about it, you can pause the video. Have you noticed that this part is basically alpha sub d? Right, so we can see this case, alpha sub d does depend on the document, right? Because this length depends on the document. Whereas in the linear interpolation, the JM smoothing method, this is a constant